This is Dr. Shankaraiah from Department of Physics. Today I am going to, in this presentation I am going to discuss about Module 1. In Module 1 I am going to discuss about Bravais lattices and crystal system. So this is the topic of today's presentation. So before going to discuss about this in detail, first we need to know what are these Bravais lattices. So Bravais introduced the concept of space lattice in the study of crystal structures. A three-dimensional space lattice is generated by repeated translations, right? The concept of space lattice is first introduced by Bravais, and a three-dimensional space lattice we have discussed in the earlier couple of earlier presentations. We discussed about this space lattice and how do we generate the space lattice, right? So space lattice is generated by repeated translations in 3 dimensions. That one would expect many such lattices can be generated using these repeated translations. Okay, so when we have discussed about how to generate this space lattice, we have discussed that we use translation, and you can use translation in one direction, and you will generate a row of points. You can from starting from every point you can generate a 2-dimensional lattice, right? So you can generate a 2-dimensional lattice, and you can generate in another dimension, not in the same plane, but in another plane you can generate. You can again use this repeated translation to generate a 3-dimensional space lattice. Okay, so can we? So if we have this in mind that okay, we can use repeated translations and we can generate so many number of lattices, but that is not correct. So that is why one would expect that many lattices can be generated using repeated translations. But in 3D, there are with the different and primitive and non-primitive cells, right? So we know that what is a primitive cell? Primitive cell is the unit cell which has only one lattice point per unit cell, and non-primitive unit cell is the one which is going to have more than one lattice point per unit cell. Okay, so primitive cell and non-primitive cells we have discussed in the other presentation, right? Primitive cell is the one which has one lattice point per unit cell. So this is if there is only one lattice point per unit cell, we are going to call that unit cell as primitive unit cell. Non-primitive unit cell. You can also have non-primitive unit cell. Okay, so non-primitive unit cell is the one which has more than one lattice point. So you can have 2 or 3 or more, 3 or so on and so forth lattice points per unit cell. In a unit cell, if there are more than one lattice point per unit cell, for example 2 lattice point per unit cell, then that unit cell is going to be called as non-primitive unit cell. So using repeated translations and primitive and non-primitive unit cells, one would expect that we can generate so many number of lattices, but that is not possible. However, Bravais showed that there are only 14 different ways of arranging identical points in 3D space. So immediately Bravais showed that okay, your imagination is not correct, that you cannot generate so many lattices with the repeated translations and primitive and non-primitive unit cells. You can generate only 14 types of lattices in 3 dimensions, satisfying the condition of periodicity, so that they are in every way equivalent in their surroundings. So we know that crystal has a regular periodic arrangement of points. If you look at any point in the crystal, it will look similar at any other point. So the neighborhood is same at every point. So these lattices, these space lattices must satisfy that condition that every point looks same compared to any other point. So the surroundings to every point is equivalent. So satisfying these condition of periodicity, Bravais showed that you can generate only 14 different types of space lattices. Okay, so you cannot generate so many lattices using just repeated translations and primitive and non-primitive unit cells. You can generate only 14 different types of space lattices in 3 dimensions, which will satisfy the condition of periodicity. Okay, So these 14 types of arrangements are called space lattices or Bravais lattices. So Bravais observed that you cannot generate many different types of lattices with primitive and non-primitive unit cells, but you can generate only 14 types of arrangements of points, and those 14 types of arrangements are called as space lattices or Bravais lattices. There are 7 primitive cells and 7 non-primitive cells. Okay, so using in these 14 types of unit cells or lattices, there are 7 primitive cells, 7 primitive lattices, and 7 non-primitive lattices. Okay, with the 14 types of lattices and on the basis of primitive cell, crystals are grouped into 7 systems. Right. So Bravais showed that there are only 14 types of space lattices are possible, and these 14 types of space lattices are also called as Bravais lattices. So out of these 14 Bravais lattices or space lattices, 7 are primitive lattices and 7 are non-primitive lattices. We know that what is a primitive lattice or primitive unit cell, which has only one lattice point for unit cell, and we will see what do you mean by one lattice point for unit cell. And non-primitive unit cell means you are going to have more than one lattice point per unit cell. So with the 14 types of lattices and on the basis of primitive cell, crystals are grouped into 7 systems. So using these primitive cells, you can generate 7 different types of crystal systems. Okay, so these 7 types of crystal systems are cubic crystal, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and trigonal. Okay, so these are the 7 crystal systems. So this trigonal is also called as rhombohedral crystal system. Okay, so using 14 different types of Bravais lattices, you can generate 7 crystal systems. Now let us discuss in detail these crystal systems. Okay, starting with the cubic crystal system. In cubic crystals, the crystal axes are perpendicular to one another. Okay, so in cubic crystal, the crystal axis, we know that there is A and B and C, right? A, B, C. These are called crystal axis or axial lengths. Axial lengths. ABC are called as axial lengths. So in cubic crystals, these crystal axes are perpendicular to one another. All these axial lengths are perpendicular to each other. So if it is A, B, C, all these 3 are perpendicular to each other in cubic crystal. So and the angle, so if because they are perpendicular to each other, the angle between these, so the angle between A and B, the angle between B and C, and the angle between C and A, alpha, beta, gamma, these angles are equal to 90 degrees because they are all perpendicular to each other. All these 3 axes are perpendicular to each other. Okay. So the length of the primitives, edges of unit cells or the primitives, is same along the 3 axes. So that means the axial lengths, right? So the axial lengths are equal. A equal to B equal to C. This is B and this is C. So A equal to B equal to C. All the axial lengths are same, and all the axes, all these crystal axes, crystal axes are perpendicular to each other. So if I say this is X, Y, Z, A, B, C are the lengths, right? So these 3 axes are perpendicular to each other. Okay. So cubic lattice has 3 possible types of arrangements. Okay, cubic crystal system is having condition that all the axial lengths are equal, A equal to B equal to C, and all the interaxial angles are perpendicular to each other. So that means alpha equal to beta equal to gamma equal to 90 degrees. Okay, so this is the cubic crystal system, and this cubic crystal system has 3 possible types of arrangements. Okay, so simple cubic, which is called cubic P, cubic primitive, and body centered cubic, which is cubic I, and face centered cubic, which is cubic F. So the cubic crystal system can have 3 different types of arrangements. You can have simple cubic, you can have body centered cubic, and you can have face centered cubic. Okay, so we will see what these three cubic lattices in detail in other coming presentation. Okay, today we are going to discuss only about these 7 different types of crystal systems that are possible with 14 types of Bravais lattices. So this is the cubic crystal system, and these are the 3 different types of arrangements of cubic crystal system. So this is cubic, simple cubic. Okay, so simple cubic, cubic P, simple cubic, that means P means for primitive. So you can have only one unit cell, one lattice point for unit cell. You can see, as you can see here clearly, and we will discuss later in detail. And this is body centered cubic lattice. Okay, body centered cubic lattice, and this is face centered. Okay, F for face centered, P for primitive, and I for body centered cubic lattice. Okay. So these are the 3 possible arrangements of cubic crystal system. So in a cubic crystal system, there is only one primitive crystal and 2 non-primitive crystals, right? So one primitive and 2 non-primitive crystal systems. We will see next. Okay. So simple cubic crystal system is also called as cubic primitive lattice. It has lattice points at all 8 corners of the unit cell, right? So simple cubic, if you see, there are 8 one lattice, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 lattice points for 8 corners of this cubic unit cell. Okay, so that is simple cubic unit cell. Body centered cubic unit cell, which is called cubic I lattice. It has a lattice point at all the 8 corners of the unit cell and 1 lattice point at the center of the body. So 8 corners, you have 8 lattice point, and there is 1 point at the center of the unit cell, right? Now, face-centered cubic lattice. Face-centered cubic lattice has 8 lattice points at 8 corners of the unit cell and 1 lattice point each at the center of 6 faces of the cube. Okay, so here, so you have 8 lattice point at 8 corners, and apart from this, you have 1 lattice point at each face, at center of each face. So there are 6 faces. So you have 6 lattice point at 6 faces. Okay. So comparing to this, you have 8 corners, 1, 2, 3, 4, 5, 6, 7, 8. And apart from this 8 corner points, you have 1 lattice point at the center of the one face. Similarly, you have one more you have here, one more you have here, 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 and here. So there are 6, 1, 2, 3, 4, 5, 6. 6 lattice points at the center of each face of the cube, right? So these are the 3 possible arrangements of a cubic crystal system: simple cubic, body centered cubic, and face centered cubic. Okay, so this is what we have discussed. Now coming to the second crystal system, which is called tetragonal crystal system. So the first one is cubic crystal system, and the second one is tetragonal crystal system. Okay, in tetragonal crystals, the crystal axes are perpendicular to one another. So all the 3 axes of this tetragonal crystal are perpendicular to each other. So length, so this is x, if y, z, 3 axis, and the axial length is a, b, c. So all these axes are perpendicular to each other. So alpha, beta, gamma is equal to 90 degrees. All these crystal axes are perpendicular to each other. So the angles between them is equal to 90 degrees. So the lengths of the edges of the unit cell along 2 axes are same, but the edge along the 3rd axis is different. So A equal to B, suppose if I take axial length along y axis is B, along x axis is A, and along z axis it is C. So the axial lengths along xy direction, along 2 axes, the axial lengths are same. So A equal to B, but they are not equal to C. Okay, so this is the condition for the axial lengths. Okay, so for the tetragonal crystal system, the condition is that A must be equal to B and it's not equal to C. So 2 axial lengths are equal, but that is these axial lengths are not equal to the 3rd axial length. And the angles are all perpendicular. All the crystal axes are perpendicular to each other. So alpha equal to beta equal to gamma is equal to 90 degrees. Okay, so this is the condition for tetragonal crystal system. Tetragonal lattice has 2 possible types of arrangement. One is simple tetragonal system and body centered tetragonal system. Okay, so even in tetragonal crystal system, you have one primitive lattice. So simple tetragonal system is a primitive lattice, that means it has only one lattice point per unit cell, and non-primitive unit cell is the body-centered tetragonal system. Okay, so these are the two tetragonal crystal systems. So primitive tetragonal or simple tetragonal and body-centered tetragonal crystal system. Okay, so simple tetragonal lattice has lattice point at 8 corners of the unit cell. So 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 lattice points at 8 corners of this lattice, and that is simple tetragonal crystal system. And body-centered tetragonal lattice, it has a lattice point at all 8 corners of the unit cell. 1, 2, 3, 4, 5, 6, 7, 8. You have 8 lattice point at 8 corners, and apart from these 8 corners, you have one lattice point at the body centered. Okay, so that is why this is called body centered tetragonal lattice system. Okay, so for tetragonal crystal system, you have one primitive and one non-primitive unit cell. Okay, so the third crystal system is orthorhombic crystal system. Right. So in orthorhombic crystals, the crystal axes are perpendicular to one another. That means alpha equal to beta equal to gamma equal to 90 degrees. So all the crystal axes, the 3 crystal axes, X, Y, and Z. These 3 are perpendicular to each other. So the angles between these axes are alpha, beta, gamma, and alpha equal to beta equal to gamma equal to 90 degrees, because all these 3 axes are perpendicular to each other. But the lengths of the edges of the unit cell along 3 axes are different. So if I take A along X, B along Y, and C along Z, the axial lengths are different. Okay, so A is not equal to B is not equal to C. The axial length. So the condition for orthorhombic crystal system is the axial lengths A and A is not equal to B is not equal to C. All the axial lengths are different, and the angles alpha equal to beta equal to gamma is equal to 90 degrees. Right. So this is the condition for orthorhombic crystal system, and orthorhombic lattice has 4 possible types of arrangements. Okay. So simple orthorhombic system, base-centered orthorhombic system, body-centered, and face-centered. So up to now we have only simple, body-centered, and face-centered. Now the new one is base-centered. So that is C. So orthorhombic crystal system has 4 different types of arrangements possible: simple orthorhombic crystal system, base-centered orthorhombic crystal system, and body-centered orthorhombic crystal system, and face-centered orthorhombic crystal system. So out of these 4 possible arrangements for orthorhombic crystal system, 1 is primitive and 3 are non-primitive unit cells. Yeah, so these are the 4 orthorhombic crystal system: primitive, base-centered, body-centered, and face-centered. Right? So these are the 4 different types of arrangements for a orthorhombic crystal system. Okay, so this is the discussion. So simple orthorhombic lattice has lattice point at 8 corners of the unit cell. So simple orthorhombic 1, 2, 3, 4, 5, 6, 7, 8. So you have a lattice point at each corner. So 8 lattice point at 8 corners, right? So base-centered orthorhombic lattice, it has lattice point at 8 corners of the unit cell and 2 lattice point, 1 each at base and top of the body. Okay, so now, in base-centered orthorhombic system, you have 8 lattice points, 1 at 8 corners. So at 8 corners, you have 8 lattice points, 8 points, and apart from these 8 corner lattice points, you have 1 lattice point at the top of the crystal system and at the bottom. So at the base and at the bottom, you have 2 lattice points. Okay, so this is base-centered orthorhombic lattice. So in base-centered orthorhombic lattice, you have 8 lattice point at 8 corners and 1 each at base and top face of the body. So bottom face of the body you have 1 lattice point, and top face of the body you have 1 lattice point for base-centered orthorhombic lattice. Coming to the body-centered orthorhombic lattice, it has lattice point at all 8 corners of the unit cell and 1 lattice point at the center of the body. So this is the body-centered orthorhombic lattice. So you have 8 lattice points at 8 corners and you have only one lattice point at the center of the body. Okay, so this is body center orthorhombic lattice, and the last one is face centered orthorhombic lattice. It has lattice point at all 8 corners of the unit cell and 6 lattice point, one each at the center of 6 faces of the unit cell. So this is the face centered orthorhombic lattice, and you have 8 lattice point at 8 corners of the unit cell, and apart from the 8 corners of the unit cell, you have 6 lattice point at 6 faces. Okay, 1, 2, 3, 4, 5, 6. Right. So these are the points at the faces. 6. So this is the face centered orthorhombic system. So orthorhombic system has 4 different types of arrangements: simple orthorhombic system, base centered orthorhombic, body centered orthorhombic, and face centered orthorhombic. Out of 4, you have 1 primitive and remaining 3 are non-primitive unit cells. Coming to the 4th crystal system, which is monoclinic system. So monoclinic crystal system, out of the 3 crystal axes, 2 are not perpendicular to each other, but the third one is perpendicular to both of them. Okay, so you have 3 crystal axes, X, Y, and Z. So out of these 3, 2 are perpendicular to each other. So alpha is equal to gamma is equal to 90 degrees. So alpha, and this is okay. So let me put this as gamma. So alpha, gamma are perpendicular to each other, but beta is not perpendicular to remaining 3. So okay, so alpha is equal to gamma equal to 90 degrees, but not equal to beta. Only 2 axes are perpendicular to each other. So the 2 angles. So alpha, the angles between these two, x, y, is these 2 axes are perpendicular to each other, and so we have alpha is equal to 90 degrees, and gamma, for example, that is between x and z. So that is also perpendicular to each other, so that is 90 degrees, but the angle between y and z, which is beta, is not 90 degrees. So alpha is equal to gamma is equal to 90 degrees, but not equal to beta. And the coming to the lengths of the edges of the unit cell along the 3 axes are different. That is, A is not equal to B is not equal to C. All the axial lengths A, B, C. All the axial lengths are different for a monoclinic system, and only 2 angles are equal to 90 degrees, and the third one is not 90 degrees. So monoclinic crystal system or lattice has 2 possible types of arrangements, right? So I am saying crystal system and lattice. So we are using lattices, and we are using Bravais lattices and to construct a crystal system, right? So whether I say crystal system or lattice here, it is fine. So it is easy to understand, right? So I am using lattice, 14 different types of lattices to discuss about 7 crystal systems. And 14 different types of lattices are the simple, body center, base centered, and face centered lattices. Okay. So this monoclinic crystal system has 2 types of arrangements, that is simple monoclinic, which is a primitive unit cell, and base centered monoclinic system. So monoclinic has 2 possible arrangements, simple and base centered. Okay, simple monoclinic lattice has lattice point at 8 corners of the unit cell. Okay, so simple as so that is here only. So simple monoclinic lattice has 8 lattice point, 8 corners of the unit cell. Coming to the base center, you have 8 lattice point at 8 corners and 2 points at the top and bottom of the bottom faces of the unit cell, right? So one each at the base and top of the unit cell. So this is base centered, right? So monoclinic has 2 types of arrangement: simple monoclinic lattice and base centered monoclinic lattices, right? So triclinic system. In triclinic, coming to the fifth one is triclinic system. In triclinic crystal systems, none of the 3 crystals axes are perpendicular to any of other. Okay, all the crystal axes are not perpendicular to each other. Okay, so x, y, z. So if you look at the angles alpha, beta, and gamma, all of them are not perpendicular to each other. So that is why alpha is not equal to gamma, beta is not equal to gamma, not equal to 90 degrees. So they are not equal to 90 degrees. The lengths of the edges of the unit cell along the 3 axes are different. Okay, so triclinic system has the very least symmetry. So all the three angles are not perpendicular and all the three axes are also not equal. Okay, so this is the condition for the triclinic system. All the three axial lengths are not equal and all the angles are not all the angles are not equal to 90 degrees. That means crystal axes are not perpendicular to each other. So triclinic lattice has only one possible type of arrangement, that it is simple triclinic system, which is primitive. Okay, so simple triclinic has only one type of arrangement, and which is called simple triclinic system, triclinic lattice, and it is also a primitive lattice unit cell, and it has lattice point at all 8 corners of the unit cell. Okay, so this is the triclinic lattice. It has one lattice point at all 8 corners of the unit cells. Okay, so this is the simple triclinic lattice system. Coming to the sixth one, which is trigonal or rhombohedral system. Okay, so in trigonal crystals, the angle between each pair of the crystal axis is same, but not equal to 90 degrees. Okay, so the angle between each pair of crystal axis is same but not 90 degrees. So that is alpha is equal to beta is equal to gamma is not equal to 90 degrees, but it is less than 120 degrees. If you look at any pair of the axis, they are not perpendicular to each other. So they are the angle between any two crystal axes is not 90 degrees, but it is less than 130. It is less than 120 degrees. Okay, and the length of the edges of the unit cell is same along all the three axes. Okay, so it has all the three axes axial lengths same. That means A equal to B equal to C. So this is x-axis, y-axis, and z-axis. If I take the axial length along x is A, along y is B, and along z is C, all these three axial lengths are equal. So A is equal to B is equal to C, and the angle is not 90 degrees. The angle between any two crystal axes is not 90 degrees, but it is less than 120 degrees. So that is the condition for trigonal or rhombohedral system. The length of the edges of the unit cell is same along the three axes. So A equal to B equal to C. Right. So trigonal lattice has only one possible type of arrangement, which is simple trigonal or simple rhombohedral system. Right. It has lattice point at 8 corners of the unit cells. So this is the simple trigonal or rhombohedral system, which is a primitive unit cell. Okay. So that is given here. Okay. So this is a simple trigonal system which has 8 lattice point at 8 corners. That is the reason why this is a primitive unit cell. Okay. Coming to the last crystal system, which is a hexagonal crystal system. In hexagonal crystals, 2 of the crystal axes are 120 degrees apart, while the third axis is perpendicular to both of them. Okay. So thus alpha equal to beta is equal to 90 degrees, but gamma is 120 degrees. Okay. So 2 of them are 90 degrees. So alpha is equal to beta is equal to 90 degrees, but gamma is not 90 degrees. So if I take this as alpha and this as beta and this as gamma, so alpha equal to beta equal to 90 degrees. So these two are perpendicular to each other and these two are also perpendicular to each other. But this one, Z and X, these two axes are not perpendicular to each other and the angle is equal to 120 degrees. So this is the condition between the axial lengths. Interaxial angles. The lengths of the edges of the unit cell is same along the axis, all the axes that are 120 degrees apart, but the edge along the third axis is different. Okay, so the A, if I take this as A and this as B and this as C, I must take now. So the length of the edges of the unit cell is the same along all the axes that are 120 degrees apart, but the edge along the third axis is different. So this one and this one is equal, but the length of these two lengths are equal, but this length is not equal to the remaining two. So A is equal to B is equal to C, but not equal. A equal to B, but not equal to C. So these are the 7 crystal systems, right? So in 7 crystal systems, if you see, we have 14 different types of lattices, right? Some of them are primitive and some of them are non-primitive unit cell. And this hexagonal lattice crystal system has only one types of possible arrangement, namely simple hexagonal lattice, which is a primitive lattice. It has lattice point at all the 8 corners of the hexagonal lattice and one each at the base and top face of the hexagonal prism. Okay, let us go to this. So this is the hexagonal lattice. So this is not the simple cubic, but here we have hexagonal lattice. Okay, so hexagonal lattice, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So there should be, yeah, sorry, I should not count this. So there are 6 here and there are 6 here. So these 6 here and 6 here. So 12 lattice point at the 12 corners of the unit cell, and you have 2 at the center of the top face and at the center of the bottom face. So this is a non-primitive unit cell, right? So we have discussed about 7 different types of crystal systems with 14 different types of Bravais lattice. Let us go back and look at how many crystal lattices we have used to generate 7 crystal systems. Okay, starting with the cubic crystal system. So cubic crystal system, we have 3 different types of lattices, right? So simple cubic lattice, face center, body centered cubic lattice, and face centered cubic lattice. So there are 3 here in cubic, and in tetragonal we have 2. So this is 4th one and this is 5th. 5. So now there are 5 lattices in 2 crystal systems, 5. And then in orthorhombic we have 4. So 6, 7, 8, 9 lattices. And then we have monoclinic 10, 11. So 12, 30 and 14. So we have 14 different types of lattices, and using these 14 different types of lattices, we have discussed about, we can combine them into 7 crystal systems. Okay, so we have discussed about the conditions for these 7 crystal systems. So all together is given here in a tabular format, right? So crystal triclinic system, you have type and number of Bravais lattices. So you have only one primitive lattice in triclinic crystal system. And unit cell axis, A is not equal to B is not equal to C. And angles between axis, alpha, beta, gamma, all of them are not perpendicular to each other. So they are not equal to 90 degrees. So monoclinic, you have 2 primitive cells and 2 non-primitive unit cells. 2 primitive unit cells and 2 non-primitive unit cells in monoclinic. And coming to the axial lengths, A is not equal to B is not equal to C, but alpha equal to gamma is equal to 90 degrees, which is not equal to beta. Okay. So orthorhombic crystal system. Orthorhombic crystal system, you have totally 4, right? Out of 4 you have you have one primitive and 3 non-primitive unit cells, right? So yeah, so and coming to the axial lengths, A is not equal to B is not equal to C, and all the angles are equal, perpendicular to each other. So all the angles are equal to 90 degrees. So the crystal axes are perpendicular to each other and angles are equal to 90 degrees. Tetragonal. So in tetragonal you have one primitive and one non-primitive unit cell. So and axial lengths, A is equal to B but not equal to C, and all the crystal axes are perpendicular to each other, so angles are 90 degrees. Cubic, you have one primitive and 2 non-primitive unit cells. So A equal to B equal to C, and alpha equal to beta equal to gamma equal to 90 degrees. All the crystal axes are perpendicular to each other. Hexagonal, you have one primitive and one non-primitive. A is equal to B but not equal to C. Alpha equal to beta equal to 90 degrees, but gamma is 120 degrees. Coming to the last one, trigonal, which is simple. Trigonal, you have only one, right? So that is trigonal. If you go back to the trigonal, you have only one crystal lattice, which is non-primitive, and A equal to B equal to C, and alpha equal to beta equal to gamma, which is not equal to 90 degrees, but it is less than 120 degrees. So out of all these 14 crystal system, you have 7 primitive lattices and 7 non-primitive lattices, right? So in each of them you have one primitive lattice at least. Some of them you have two, one, right? So totally you have 7 primitive unit cells and 7 non-primitive unit cells. So combining all these 14 lattices, you can generate 7 crystal systems. So to summarize, we have discussed that using repeated translations, you cannot generate so many number of lattices. You can generate only 14 types of lattices. That is done by Bravais. Bravais said that you cannot generate many types of lattices using repeated translations, and primitive and non-primitive unit cells, you can generate only 14 types of Bravais lattices. And using these 14 types of Bravais lattices, you can discuss or describe about 7 crystal systems, right? So we have discussed about all these 7 crystal systems and with 14 types of Bravais lattices. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.